Alright, so now we'll begin a transition into really the second part of the class where we really go the opposite way. So you can see just from the title alone that we're talking about this notion of antiderivatives. So that should lead you to believe that we're basically going backwards. So the nice little thing you can do to kind of warm up is think about this question, right? If the acceleration of an object is given as negative 9.8 meters per second squared, what would velocity have been? And that's thinking backwards, right? Thinking from the idea of we start with position, derive that, go to velocity, derive that, go to acceleration. So if acceleration is negative 9.8, think about where that came from, right? The function before it, which was velocity, would have to be negative 9.8, let's say t. And that's kind of where we're going today, right? If we derive negative 9.8 t, we'd get negative 9.8. So the idea here is to figure out not only what an antiderivative is, but exactly how do I find one. So as you can see here in the fill in the blanks, right, what we did was find an antiderivative, and the process we used, as you can imagine, is called antidifferentiation. So if you think about it, how many other possible velocity functions could we have had there? Well, really, the answer is infinitely many. So infinitely many. All right, now why is that? Well, because if you think about it, this velocity function we came up with before could have been negative 9.8 t plus 40 or minus 8 or anything like that. So what we're going to do to account for that is we're going to add a plus c, which is a constant. And that has a specific name. It's called the constant of integration. And we'll get a little bit more into this word integration. Integration is just an alternative term for antidifferentiation, right? So the reason that this doesn't violate any rules is because the derivative of any constant would have been 0, right? So that really allows us the flexibility we need. Now, how would we know if this was something specific? Well, we'll get into that a little bit later. How would we know if this specific velocity function was plus 8 or minus 16 or whatever it might be? And we'll get into that with some initial conditions later on in the lesson. So let's just look at these rules we see here on page 2. We have the idea of basically, again, going backwards. So you can see, I didn't take a picture here, but you can see that the integral or the antiderivative of 0 would have to be c. That's what we just talked about. You can see we have a power rule in here. We have an integral for e. There's a lot of different things there. So we're really going to use these rules to help us out with some basic examples here. So if you ask me to find the integral of dw, remember this w has some significance. It's the variable of integration. That means my answers would have to have w's in them, right? So you're thinking like this. You're thinking to yourself, okay, technically there's like a 1 there. Whose derivative is 1? And so we're used to saying x, but in this case we'd say w, because the derivative of w or x or y or any of those things would be 1. Now what we do have to make sure is we add the plus c here, because if this was the original function, the derivative of that would be 1 and the derivative of c would be 0, so it gets you right back to where you needed to be. Let's look at a second example. The integral of x plus 2. Well, what we know here is this is the same thing as the integral of x, right, plus the integral of 2. So what that allows me to do is treat each piece of this separately, just like when we were doing derivatives. So the integral of x would be a power function, x to the first. So that would turn into x to the second over 2. And if you look at that rule, you can kind of look above here, you can see it's this rule, x to the n. So we're adding a power and dividing by the new power. That is exactly the opposite of what we did for derivatives, right? Where we brought the power down and subtracted. So we're doing the exact opposite. So that'll turn into x squared over 2. 2 will come from 2x, right? Think about it. If you derive 2x, you get 2. And then we still have to always add plus c. So the good news is, as we're doing this, it's a very new process, but it's backwards. So it's actually should be a little bit familiar. How do I know if I'm doing this correctly? Right? Well, look, take a look at your answer. If you derive this, if we treat this as y, right, then when we derive that, what we get in the original integrand, that should represent y prime. Oops. So look here, right? Look right in here for y prime. Okay, let's try example 3 and example 4. Now, if you feel good, you can kind of move on here. But basically, we're going to have 3 different pieces to worry about, right? So the integral of 3p to the 4th would be 3p to the 5th over 5. The integral of 5p squared would be 5p to the 3rd over 3. And the integral of p would be p squared over 2. And then, as always, adding the plus c. So using those power rules. And then finally, example 4, t to the 3rd over 3. Now this is the tricky one, right? Integral of sine. So you're thinking, what did I derive to get sine? And the answer is, it's really negative cosine. And then, of course, plus c. So the cleaner answer here would basically be 1/3 t to the 3rd plus cosine of t plus c. So the good news is we're not doing too much. We're just introing this kind of thing right now. We're going to go over any questions you have in class. We're going to do one more slide, though, because I want to take a look at just some awkward examples that you might have to think a little bit about. So one of the things you might want to consider doing is rewriting an integral, right? Taking what they've given us, rewriting it into something more user-friendly before we integrate it. So for this first one, for instance, it would probably be better if I wrote that as x to the negative 3rd, right? That allows me to use my power rule, in which case I get x to the negative 2nd, right? You're adding a power, dividing by the new power, and of course adding c. Now when we talk about should I simplify, obviously that's okay, you know, this answer we have, but if you want to write it a little more formally, right, it would probably look like that. Right? Either way, obviously, is acceptable. So let's talk about the rewriting process again, right? Second one. How about we rewrite this as the integral of t to the 1/2? Again, allowing me to use the power rule. And I'll finish this one up as well for you. So we should get t to the 3/2 over 3/2 plus c. If we simplify that, that's basically just 2/3 t to the 3/2 plus c. Okay, so in the interest of time, not to make too long of a video here, for the last 3, why don't you try to rewrite them and then simplify them. Pause the video for a second. When you're ready, go ahead and restart it, and I'm going to give you the rewrite version and the simplified answer. Alrighty, so for our first one here, the rewrite would have been the integral of x to the 1/2 plus x to the negative 1/2. And eventually that would get us to a final answer of 2/3 x to the 3/2 plus 2x to the 1/2 plus c. Fourth one would actually be easier if we rewrote it as secant x tangent x, so a little use of identities there. And then that would allow you to just say the answer is secant x plus c. And then similarly for this last one here, best thing you could do here is distribute, so you have secant theta tan theta minus secant squared theta. That would be kind of how we rewrite that. And let me just change the color here so it's easier to see. That's going to yield a final answer of secant theta minus tangent theta plus c. Again, we'll go over whichever one of these we need to in class. We're going to stop the video there. We're going to pick up everything here from the error analysis on when we get together again.